Bismillahirrahmanirrahim. Assalamu alaikum viewers. First of all, I would like to thank you a lot for giving me a trust and taking this decision to watch the second video of our free video series. So here you can see from the heading it's quite clear that we are going to understand in this video the integration through substitution process. So basically there are two types of substitution, that what we call u-substitution and trigonometric substitution. So here in this video we are going to focus on the first type, that is u-substitution here. Okay, so actually when the need of using substitution method comes in integration, that whenever you experience, or whenever you just see the integrand which is quite typical and it's hard to integrate it directly, then in that case you just try to use u-substitution process. Or if you're having an integrand which is in the form of a product of two different functions, such that one function is the derivative of the other, or vice versa, like if g of x might be the derivative of f of x, or your f of x might be the derivative of g of x. Okay, if this is the case, then in that case you are going to use your substitution process. Here basically when it's a kind of traditional approach, you can say, that we just replace the original variable, whatever the variable is going to be in the integrand, we just replace it by our u variable. So that's why we just make it a name as u-substitution. Though you have freedom, you can replace the original variable by any other alphabet like that. So it's a full freedom, by the way, but as it's a tradition, that's why we just use u here in substitution process. Okay, so here we are going to pick up few examples of few questions, and we just try to solve them, and belonging to both definite and indefinite integrals, and we just use this u-substitution methodology and try to see how it is helping us out in integration. Okay, so let's start. Okay, so here you go, your very first question, and you can see that you're having 2 in the denominator here. So we just take out our simple constant number outside the integral. That's what you call basic rule. So now the integrand that you can see here is having a form something like this. You can see you cannot modify this integrand into a simpler form so that you could find it easy to integrate in its original, keeping its original variable. Okay, so it's not possible right now. So what you do, you are going to use u-substitution. How about if I just say that just replace your under root x or square root of x by your u. Okay, so let u is equals to under root x here. Instead of writing under root x, I better write x power half. So it is going to be it's much easier for me at the time of taking out its derivative. Now you see this is my substitution process has just begun. Okay, and now what I do, I'm just going to differentiate both sides of this. I just call it equation number 1, and I'm going to differentiate both sides of this equation number 1 with respect to the original variable, that is your x. Okay, so we just derivate it now with respect to original variable. Okay, so now you are well aware of taking out the derivative of x power n, so we just take that formula and we just try to do that. So it's gonna be half x half minus 1 and then you just take out, obviously you see we just apply chain rule in every step of our derivative, but here already you can see that the base is already x. So if you just apply the chain rule on this base, definitely it's giving you 1. So as it is giving you 1, that's why we don't generally mention such kind of chain rule. Okay, so it's just, you can understand in a default that it is there, but it is invisible because it is 1. Okay, so it's like that. So it is giving me half x power minus half, so it is giving me 1 upon 2 x power positive half, that is under root x. So now what I do, I just shift this differential dx on the other side, and it is going to look something like this. Okay, so here you see in this integrand, now just focus here. In this integrand, you're not having 1 upon under root x dx. Just half dx is available here, right? So what we do, we just shift this under root x over here towards my du, something like that. So, and half d of x will be kept as it is on its side. And as you see that under root x is equals to u, so just replace this under root x by means of your u, because of course it is now connected with your differential du, so it should be in form of u, of course. So that's it. Now as you can see, this is one step, it's done. And now we are going to transform, and we are going to change our integral limits as well. Okay, so as we know that the lower integral limit is 1 and the upper is 4, so now according to our substitution format, if my x is 1, then what is going to be the value of my u? You see, u is equals to under root x, so under root 1, so it is giving you 1. Alright, don't say that it is plus minus 1, so which one shall I take? It is positive, so just take it positive. Okay, and once when your x is 4, then your u limit is going to be under root 4, that is positive 2. Okay, so these are going to be the new limits. That's what you're going to insert. So in this way, my actual integrand is this, and I'm going to now change it with respect to my u form, and it is going to be at the place of my, if my x is 1, my u is also 1. If my x is 4, then my u is 2. Okay, and here I'm going to write my u minus 1 upon u square plus u upon u square plus u, right, times, at the place of my half dx, I will write u du, right? That's it. Now you see in the denominator, I can take out my u common, right? And that common u is going to cancel that numerator u. So we are going to do that. So integral going from 1 to 2, u minus 1, u is coming common outside, u plus 1 times u du. I'm going to cancel this u with my this u. It is giving me a form something like this, u minus 1 upon u plus u. Now you see here, I'm still unable to apply my integral directly. So what I do, I will make a little modification to this simple looking integrand. So what I do, how about if I just write it something like this? How about if I just make it a nice adjustment like this? So on taking the LCM stuff, this form is going to be obtained, right? So this is a little modification I did, and now I'm going to apply my integral separately on these two terms, and I will get my answer. So it is going to be integral going from 1 to 2 du minus 2 times integral going from 1 to 2 1 upon u plus 1 du. Okay, so like that. So now you just nicely apply your basic integral and you will get your answer. So it's going to be something like that, and this is going to be ln of u plus 1, okay, times going from limit 1 to 2 and so forth. So now we apply the limit, and this is something that we have understood quite well in the previous video if you have watched. So now here ln of my 2 plus 1, like I'm applying my first upper limit, and minus ln of my lower limit. That's it. So it is giving me 1 minus 2 times ln of 3 minus ln of my 2. Now you can see here, you can apply the major property of your logarithm, right? That was, if you remember, which was actually this, that if you're having logarithm of a quotient form, then it is going to be represented in the form of a difference of its numerator and denominator. So we are going to use this formula here. That is 1 minus 2 times ln of 3 by 2, right? And now you can see I can leave my answer here. That is also fine. I can also, if I don't like this negative sign, I can shift this minus 2 at the power place of my 3 by 2 according to your, say, another property that is an exponential property of the logarithm. If it is in your knowledge, you see that if you're having this case in the log, then it's gonna be written something like this. So we are going to use this formula here. So I can write, if this is your x, this is your n, I can apply it over here. Okay, so I have just written this form into this form. I hope it's clear. So that's what we have done, and the final form can be in a nice looking 4 by 9, and that's your answer. You can either stop here, or you can just use your calculator, get your answer in decimals. That's also fine. So that's how you do. Okay, so this is the first example, first question. Let's move to the second one. Here you go. So now here you see, as I told you in the beginning, that in two cases you just use your substitution. If it is very typical looking, you have to transform it. Then you just, I'm talking about the integrand, that if the integrand is very typical looking, you have to transform it, then you use your u-substitution. And if the integrand is in the form of two function product, in which one function is going to be, can be expressed as the derivative of the other, then you use your u-substitution, right? So you see here in this question, the integrand is the product of two different functions, right? So you can see here that if I just pick up my g of x, then the derivative of the g of x is going to provide me f of x here. Okay, so you see, if I'm going to use my u substitution here, and I will replace my x cubed minus 2 with my u, and then I just apply the same process that I did in the first question, that I will take the derivative both sides of this first equation with respect to the original variable, which is my x. So, and you can see that this is an indefinite integral, it's not having the limits, so there's no need to transform it. We will get our answer having some constant attached there. Okay, so let's do it here, and you see that du by dx is equals to, now you just apply your derivative on x cubed and the derivative on your 2, so you're getting 3x squared minus 0, that is of course simply 3x squared. So you see your du is equal to 3x squared dx. So you see 3x squared dx is going to be replaced by your simple du. Okay, so over here, let's continue. It's going to look something like this. This is my u power 4. 3x squared dx is going to be replaced by my du. Now I apply my simple integral on the polynomial. So it's going to be u4 plus 1 upon 4 plus 1 plus some constant, as I'm not having integral limits. That's why I just apply this constant here for the adjustment, and it's going to be u power 5 upon 5. This is it. Now as I'm not having the limits, so I'm going to restore my original form, and the final answer looks something like this, whole power 5. Okay, plus some constant. So this is your nice answer of this question. Okay, I hope it's clear. Now let's pick up the third question now. Okay, this is our nice third question. This is also an a definite integral. Now you might be thinking that here the integrand is the product of two functions. Okay, so but you see, none of these two functions is the derivative of the other. Okay, so how to modify? All right, so if you just let this x equals to u, then it's not gonna work. You again have to apply the substitution. We are not in mode to apply substitution over substitution, right? So here I recommend you to assume or just replace your x minus 1 by your u. Okay, so this is gonna help, and we will get our answer in less number of steps. So when we assume like that, now it's easier for us to handle this integrand. So we just take the derivative. So derivative of our x is gonna be 1, derivative of our 1 is gonna be 0, so simply 1 is over here, and then we just shift this dx over here, so du is equals to dx. So we are going to replace this dx with our du. Okay, and as far as we are going to change the limits, of course. So if your x is equals to 1, the lower limit, then what is going to happen with your u? Your u is going to be 1 minus 1, which is your 0. Here I just substitute my x value here, and I just got the u answer. Okay, in the same manner, if your x is equals to 5, then u is going to be 4, of course, right? So it's going to be 4. So these are the new limits that we are going to use. Okay, so let's do it over here. So what happens is integral is going from 0 to 4. Now you see, at the place of your x, you are going to write u plus 1, because here you can see that x is equals to u plus 1. So wherever you're having your x, you just write u plus 1 there. Yeah, and at the place of your x minus 1, it's going to be under root u. So instead of writing under root u, I prefer to write u power half, so that on multiplication it will be easier for me to handle the powers, right? So this is it. Now what I do, I'm going to multiply this u power half by both these two terms inside the bracket, and I'm going to get a nice integrand that I'm going to integrate later on. So once u multiply by u power half, so I'm just going to add up the powers, plus u power half into 1 give me u power half. I hope it's fine, like that. And now it's we just take the LCM over here, is going to give me 3 by 2. I hope you're aware with the LCM work. So u power 3 by 2 du plus u power half d. Okay, now I'm going to integrate this integrand, each term of the integrand individually. So a little here, so that's how it's going to look like. And then you apply the formula of your integral of xn, and you will get your answer. So it's going to be 3 by 2 plus 1 upon 3 by 2, going from 0 to 4, okay, plus u half plus 1 upon half plus 1, going from 0 to 4. And now we are going to nicely apply our upper and lower limits. So let's see how it looks like and what it is going to give us. So it's u5 by 2, I'm taking out the LCM, plus u3 by 2 upon 3 by So you see, you have to be very exhaustive in each and every step. You must not miss anything. Don't be that much direct, otherwise you won't be able to learn the things well, right? That's why I'm just showing you each and every step here. Otherwise I could do it directly, but if I do, it will pass over your head. Now you see, just move, just shift this constant values in the denominator, which is in the fraction form, so it will be turn into its reciprocal. It will look something like this. And like that. And now the stage comes when I am going to apply my nice upper and lower limits. So it's 2 by 5, and you see 4 is actually 2 square, so instead of writing 4, just write 2 square so that you can handle the overlap powers like that. Okay, and 0 power, whatever the power you have on 0, the answer is always 0. It's quite obvious. So okay, so this is the first fundamental theorem of calculus we are using, that we have discussed in the first video. If you haven't watched that video, then I recommend you to watch that first for better understanding. Okay, now 2 power half minus 2 power 5 minus 0. Okay, and I better use here round brackets now. There is no need to apply square brackets now. So I just use my nice round bracket. Overlap powers are going to cancel the numerator and denominator 2 here, and simply 2 cubed minus 0 is left. So what I'm having here is this 2 multiplied by 2 power 5 give me 2 power 6 upon 5 plus 2 power 4 upon 3. Okay, now here you can notice that I am having 2 power 4 coming common from both these fractions. So I'm having 2 square upon 5. Now I am directly going to apply my LCM work, and 2 power 4 is what? It is 16, yeah, and is 4 by 5 plus 1 by 3, so 16 times it is 15, 12 plus 5, and it is giving me 16 into 17 upon 15. I just used my calculator and I got the answer, which is this is the final steps. I'm using equals to sign, so it is giving me 18.13 and square units. Okay, so I'm writing square units here. You might be thinking why she's doing that, why simply not you end up the answer over here. What's the use of writing this? Because you know that definite integral explains here area under the curve. I hope you remember that in the first video. So that's why I use the square units here. Okay, now that's the answer. I hope it's clear. Now let's see one more question. Now here you go, a nice question in which you are provided here a nice graph belonging to this function. Okay, and we need to find out the area of this shaded region. Okay, it's going from 0 to it's going from -1 to 1. Okay, there are two ways of doing this. You see, either you find out area of the region from -1 to 0, and then find out area under the curve from 0 to 1, and then add up these two areas, or you can integrate from -1 to 1, and you are going to get your total area of the shaded region as well. Okay, there are two ways of doing that. So I'm just picking up my second method, and I'm going to integrate directly from -1 to 1. Okay, I'm just selecting the second way because over here you're going to learn one new thing. Okay, so a new property, or you can say a new theorem of the integration that I'm going to use here. So you see here, let's start the solution. You see its area is actually over here is going from -1 to 1 times y dx, or f of x dx, where my y is this. You see, I'm going to use my nice substitution process here as well. Okay, so it's Very delicious question, I must say. So you see that if I just pick up this expression and I just derivate it, I'm going to get 2x. Okay, and from there I can adjust this term n dx with respect to that derivative. Okay, so what I do, I'm going to assume, or I'm going to replace my x is square plus 1 with my u. Okay, and once when I take the derivative, I will take derivative both sides with respect to my original variable x. Okay, dx. So it is giving me 2x equals to du by dx, and this dx is going to move here, as you see. So this thing shows that my du is equals to 2x dx. Alright, so from my 6x, I will just take out my 2x and 3 will be kept outside, and 2x dx will be replaced by my du. One thing is done. Now I'm going to change my limits here, that if my x is equals to minus 1, then what happens? Then my u is equals to minus 1 square plus 1, that is giving me 2, of course. And if my x is equals to 1, then u is, whoa, it's again 2. It's again 2. So how could that be? Then in integral I just use same limits at the upper and lower position. Of course it's gonna devastate my integration process, right? In order to help this situation out, what I do, I'm going to use here a nice theorem of my integration, that if I'm having a symmetrical curve whose area I need to find out, either like that, maybe a symmetrical curve. See, both these parts are same. So you see, if I'm having a curve like that, going from, for example, minus 2 to 2, instead of using numbers, I better use a variable, minus a to a. Okay, so whenever you are having symmetrical regions, you have to find the area of this whole, you have to find the area of this bounded by this whole curve and the x-axis from minus a to a. So you can notice here that this y-axis is behaving as an axis of symmetry here, right? And it is dividing this entire region into two equal looking parts, right? So how about if we just take out the area under this curve, just one part of the area under the curve, and just multiply this area with 2, so that you are going to get the area of this full region, right? So you see, whenever you are having a case like this, that these two values are just differing by the signs, and in magnitude they are same, then in that case you are going to find out your area by multiplying an integral having limits equals to half of it. Either you can take minus a to 0 f of x dx, or you can take 2 times integral going from 0 to a f of x dx. You can pick up any portion you want, take out the area, and then multiply it 2, you will get the area of the full region. So this is the concept we are going to use here. Okay, so that's what I was just trying to tell you, that there was a new theorem I would like to introduce here. So this is the one. Okay, so now what I do, instead of taking the integral from minus 1 to 1, I can take the integral 2 times integral from 0 to 1, or from minus 1 to 0. It is my choice. Okay, so I just move here, and I must drag this nice snapshot along with me because I need it a lot. So here it is. Nice adjustment here. Okay, so my area can be written as 2 times 0 to 1, okay, 6x. Instead of writing 6x, I can write 3 times 2x, and then x squared plus 1 cubed dx. Okay, so 2x dx will be replaced by my du, if you remember. So now if my limit, if my x as I told you that in the beginning, I told you that my x squared plus 1 is u. So if my x is 0 here, what is going to be my u? My u is going to be 0 squared plus 1, that is 1. Okay, and when my x is 1, my u is 2. Okay, so just remember that. So we are going to use it here. One to 2, 3 times u cube du. This 3 is going to be multiplied with this 6, and I'm having u cube du, right? Now just I apply my simple integration, and I'm going to get my area bounded by the given curve and the lines, x equals to minus 1 and x equals to 1. So that's it. So let's do it as fast as we can. So it's going to be u4 upon 4. Now I'm going to get a little direct. I'm not going to show each and everything in the working in the place of my indices. I hope you cooperate that. I just cancel this 4 with this 6 is 3 by 2. So I just write 3 by 2 outside, and then over here now I apply my theorem for the definite integrals. So it is going to be 3 by 2, 2 power 4 minus 1 by 4. So it is 3 by 2 giving me 16 minus 1, yeah. So it is giving me 3 by 2 times 15, so it is 45 by 2. And it's going to be what? It is going to be 22.5 square units. So this is the area bounded by the curve and the lines x equals to minus 1 and x equals to 1. So that's how we do. I hope it's clear. Now let's see one more example. Now here you go, nice example here once again, and now you can see how to handle this. Do you have to factorize the denominator? Are you going to have a common factor that can cancel this numerator? Is it like that? You can try it. But how to handle this same question through substitution? Is it possible or not? We are going to check it. What I do, you can see that the denominator expression is having higher degree as compared to the numerator expression. So of course, I'm going to take out the derivative of my denominator and see if that derivative is equal to the numerator expression or not. If it is, u-substitution is going to win, and we'll take the help of that. Okay, so I just let my u is equals to 3x squared plus 9x minus 1. I'm going to derivate both sides with respect to my x, my original variable. So this thing is going to give me, I just take out the derivative of my 3x squared is giving me 6x, plus derivative of my 9x is simply 9, derivative of my 1 is 0, so no need to write 0. So you can see here that if I take my 3 common outside, if I take it out, I'm getting 2x plus 3 here. Alright, so du by dx. So how about if I just shift this 3 over here at the left side and dx on the right side? I come to know that 1 upon 3 du is equal to 2x plus 3 dx. That's what I can replace. Beautiful. So now my u substitution is helping me. So what I do, I will just change these terms. So it is 2x plus 3 dx is going to be replaced by 1 upon 3 du. Okay, and it is 1 upon, this thing is my u. I'm sorry, it's du. I just wrote dx by mistake. So this is du. Okay, so now you see, you know integral of 1 upon u is log of u. So you just use that. So it is ln of u plus some constant, as it is a indefinite integral. Now you just restore the original form, and it's going to give me 1 upon 3. And before that restoration, I recommend you to just just apply this constant number at the power position of your u. So it's going to be ln of u power 1 upon 3, so that's the power of the cube root. Yeah, so just try to modify your answer the best extent as you can. So it is the cube root of your u plus c. Now restore. So it is finally ln of your 3x square plus 9x minus 1 plus c. This is the answer of this integral with the help of your u-substitution. I hope it's clear. Now let's see one last example, then we are over this class. Okay, so let's see the last example now. Okay, now this is the first part of this question. It says that you need to sketch the graph of this function from 0 to 2. This is the function that is given to me. Okay, so how I'm going to sketch it, I'm going to form a table for the values, and starting from 0 to 2, like that, little larger. I just pick up x and y, one column for the x and y, another column is for my, I just take, it's for 0, it's for 0.5, it's for 1, it's for 1.5, and this is for 2, and 2 is, space is quite large, you see. So how about if I just minimize this? That's much better. Okay. Same thing I'm going to do with the line as well. There you go. Okay, so here this is my x values, and they are going from 0, 0.5, and that's what I've decided all by myself. Okay, you have freedom to use any value between 0 and 2, and 0 and 2 definitely you have to take that. Okay, there's 1, it's 1.5 and 2. Okay, and the value of y is following this function. That's what we are using. Okay, so when you just substitute these values in this equation, you're going to get the answers like that. So I must use a different color for that. I'm not showing the calculation because it's you see, it's something quite understood. You just substitute the values of x over here in the equation, and you will get the y coordinate. Something quite basic. So we just directly write the answers. You can check it through your calculator in your free time or whatever sounds convenient to you. So that's it, 0.88 and so on. Now these are the values. Now what you do, how you're going to plot it on a plain paper. Of course, in the exams you are provided the plain paper where you have to plot. So what kind of scale shall you take? You see, the values are going from, if I talk about my y values, they're going from 0.5 to 0.8. So if you take 1 centimeter equals to 0.1 unit for the y, then you need 8 centimeter long line. Okay, and if the space is not sufficient enough, then definitely you have to shrink the scale. So how about if you just take half centimeter equals to 0.1, so the 4 centimeter long line is going to help out. So it depends. Scale values actually depends on the space of working provided to you out there. Okay, so sorry for that. So I just take here 0.5 centimeter equals to 1 unit for my x-axis, for my y-axis, and for the x-axis I'm going to take 1 centimeter equals to 1 unit. Okay, this is for the y and this is for the x. Okay, so that's it. So it's 1, it's, sorry for that, it's 0.5. 1 centimeter should be equals to 0.5 units, my bad. So it must be like that on the x-axis. 0.5 units. Okay, so this is your 0.5, this is gonna be your 1, this is 1.5, this is your 2. Okay, and on the y-axis, what you're taking half centimeter equals to 1 unit, 0.1 unit. of centimeter equals to 0.1 unit. Alright, so it's going to be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 7 and 8. Okay, then once now we plot the values, you see at 0 I'm having 0.5, must use a different color. So at 0 I'm having 0.5, so the value is here. At 0.5 I'm having 0.6, the value comes a little here. At 1 I'm having 0.7, it goes a little here. At 0.5, 1.5 is 0.8, so here. And at 2 I'm having 0.88, so it's going to be somewhere here, so it's going to be here probably. Okay, so this is it. So you see the curve looks something like that. There you go. Okay, if you want to extrapolate ahead, it's up to you, it's your choice. So you see this is it. So now you see we are going to see the next part of this question, and let's see what it is asking us to do. 0.2 point comes here a little. It is actually here, so like that's how the thing looks like, something. You can check it through your Desmos graphic calculator as well, and we can confirm our curve type. You see, that's how it looks like. You see, it's going from 0 to 2, a curve something like that. So from this portion to this portion. Alright, so it's quite clear. So we were right, our sketch was correct. So let's proceed ahead, and this is it. So now what next they are asking us to do? Let's write the second question. The second part. So now here in the second part we need to find out the area bounded by this curve, these two axes, x and y axes, and the line x equals to 2. So the line x equals 2 is actually this. That's what the line is. Okay, so we need to find out the area bounded by this blue curve, x and y axes, and this line. So this is the area that we need to find out. So actually your curve is going from 0 to 2. Okay, so we need to integrate our integrand from 0 to 2 limits, and we will get our answer within no time. So area is equals to 0 from 0 to 2. This is the integrand times dx. Okay, so here again the substitution process is applied. You can see that if you just let your denominator equals to your u, then what happens? If you take the derivative at both sides, then this derivative is going to provide you, you see, the derivative of your ex is ex, okay, and derivative of 1 is 0, of course. So you see du by dx. So this thing clearly tells us that du is equals to ex dx, right? So this thing tells me that I am going to replace this ex dx by my du. Now let's talk about the limits. So you see, limits are very clear that if my x is 0, then u will be equal to e power 0 plus 1, no matter what is going to be the base. If the power is 0, answer is 1. So 1 plus 1 give me 2, so the u will be 2. And if x is equals to my 2, then my u is equals to e square plus 1. These are the upper and lower limits. That's what we are going to use here. So let's write it a little here for you just for consistency. So it's going to be 2 to e square plus 1, these are the limits, 1 upon u du. Okay, so ex dx is replaced by du, ex plus 1 is replaced by u. This is the answer, this is the situation. And now area is going to be what? So the area is finally getting closer, so it is going to be ln of u going from 2 to e square plus 1. Yeah, so now apply your limits. It's going to be e square plus 1 minus ln of your 2. You can either leave your answer here in square units, or you just write your answer in terms of your decimals. If they specially mention in the question that write your answer up to 2 decimal places or up to few significant figures, then you have to use your calculator. So if I use my calculator now, I'm getting the answer 1.43 and so on. I just stop my answer up to 2 decimal places. In other words, up to 3 significant figures. This is my answer. So that's how we do. I hope it's clear, and thank you for watching this video to the full length. I really appreciate that. Now in the third video, we are going to understand how to integrate, how to perform the integration using by parts. Okay, so if you want to see that video, if you want to watch that, you can click the link right below this page, and you will be redirected to the third video of the free series. Thank you for being with me, and take good care of yourself, study well, score good. Allah Hafiz.